Okay, in this video, I want to go back to sort of the essence of probability. And I've said this in all of my videos so far. To calculate a probability, it comes down to counting. And that's the focus of this video. I don't think we're going to talk about probability at all. Not till the next one, but in this video, our focus is counting. So, before we talk about any specific counting techniques, let's look at a problem similar to something that we've already done. Let's say we have a club with 4 members, and we'll call them Alice, Bob, Charlie, and Dave, A, B, C, and D. Question is, in how many different ways can we choose a 2-person team to represent that club of 4 people? Well, the numbers are small enough that we could just list out all the options until we've exhausted all possibilities. And if we were to do that, Alice and Bob, Alice and Charlie, Alice and Dave, so on and so on, we get 6 options. 6 possible pairs of people. There is no 7th possible pair of names that is not already on this list. So we have 6 possible 2-person teams. Okay, let's take this one step further. Instead of a 2-person team, let's say for the same club, Alice, Bob, Charlie, and Dave, for the same club, how many different ways can we pick a president and a vice president? Okay, so now this is different. Order matters. Alice, Bob is different from Bob, Alice. So now it looks like we've doubled to 12 possible scenarios, because now Alice and Bob, this group of 2, accounts for 2 possible options. President Alice, VP Bob, or President Bob, VP Alice. Whereas before, whether it was Alice, Bob, Bob, Alice, it didn't matter. It was the same team. All right, so this is a very small example, just 4 members, and we're picking 2. But what if we did the same problem with a club of 20 members? And of those 20 members, we're picking a president, a vice president, a secretary, and a treasurer. Now, this is not something we could do right now because it's impossible to count by listing. I wouldn't say impossible, but it's logistically improbable that you would ever want to count the 116,280 possibilities by listing them one by one. And that is the purpose of this section. We're talking about counting, and we're talking about counting things that we can't list, or things that we can't count one by one. We don't care what the items on the list are. All we care about is how many items there are on our lists. And that is, again, the essence of probability is counting. All right, so let's talk about some counting techniques. In this section, we're going to talk about 3, I say several here, but we'll talk about 3 methods for finding large numbers without directly listing and directly counting. All right, so let's look at this example. Think about, you have 5 positions in line, 1st, 2nd, 3rd, 4th, and 5th. And how many different ways can you line up 5 people? So you pick one person to be first in line, you pick another person to be second, and so on. All right, so you have 5 choices for who goes first. You've got 5 people. Pick one of the 5 people to be in their first position. Now, for each of those 5 people, say person 1, person 2, person 3, person 4, person 5. For each of those 5 people, well, the first person is gone, so now you have 4 people left. And of those 4 people, you have to choose one to be second in line. So now you have 4 choices. So for each of these first 5 choices, now you have 4 choices for position 2. So if person 1 went first, you have 4 options for the second position. If person 2 went first, you have 4 more options for the second position, and so on. So now, 5 times 4 is 20. You have 20 different ways that you could pick the first person and the second person. Now, continue on with this logic. So far, there's 20 different ways to pick the first 2 people. Well, 2 people are gone. There's 3 people left. So now for each of those 20 options, you have 3 choices for who is in position 3. So that brings you up to 60. 5 choices for the first position, 4 choices for the second, 3 for the third. Now there's 60 ways to pick the first, second, and third people. I'm going to keep going. For each of these 60 options, you have 2 choices left for who will follow in position 4. All right, so the number of ways to choose positions 1, 2, 3, and 4, well, now we're up to 120. And now for each of those 120 choices, or each of those 120 ways to pick the first 4 people, you have no options left. There's only 1 person left for the 5th position. So for each of those 120 options, there's 1 person left. So the total number of ways that you could line up 5 people in order would be 5 times 4 times 3 times 2 times 1, or 120. Now it turns out there's an abbreviation, and you may have seen this before, you may have not, but instead of writing this, instead of writing 5 times 4 times 3 times 2 times 1, what if instead of lining up 5 people, what if it was lining up 20 people? You wouldn't want to write 20 times 19 times 18 times 17, all the way down to 1. So it turns out we have a nice convenient notation called factorial. And factorial notation is an abbreviation for multiplying. And the notation we use for factorial is the explanation point. So n factorial means you multiply all the numbers, starting with n, down to 1. Now what I mean by this, from our previous example, we had 5 times 4 times 3 times 2 times 1. And using this new factorial notation, that is 5 factorial. And if you type that directly into Desmos, as soon as you type 5 explanation point, as soon as you type in 5 factorial, Desmos gives you the same 120. So it just takes a second or two to calculate factorials. Whereas with a handheld calculator, excuse me, if you had to do, let's say, 20 factorial, you have to type 20 times 19 times 18 all the way down to 1. It's cumbersome, and it's actually unnecessary because we have this nice factorial notation. And just in case it comes up, we have, just so we don't have any issues with the calculations, 0 factorial is equal to 1. This just makes things run smoothly. It's like any number, let's say 5 to the power of 0 is also equal to 1. Same thing, any number to the 0 power is 1, or 0 factorial is also equal to 1. And the big result here is the number of ways to arrange n distinct objects should be, so in this case we have 7 boxes of 7 distinct different colors, and how many different ways can we stack them vertically? There's no difference here. It doesn't matter if we're talking about boxes, we're talking about people, it's the same thing. As long as it's 7 different items, like before we had 5 different people, this time 7 different boxes, it makes no difference. So you have, by the same logic as before, you have 7 options to pick the first box, then you have 6 options left to pick the second box, and you have 5 options left to pick the third box. So it's no surprise, it should be 7 factorial. And from these 2 examples, we could generalize this to any group of n distinct objects can be arranged or ordered in n factorial different ways. All right, So that is factorial. Now, so far, we've been focused here on the distinct, 5 different people or 7 different boxes. Maybe you have some repeated objects. So let's look at the word initially. If there are repeated objects, and let's say how many different ways could we rearrange the letters in this word? Well, there might be some repeats. There might be some repeated arrangements because there are some repeated objects in the set, or in this case, repeated letters in the word. What I mean by this is, let's make, so with the word initially up here, let's make the first I red and the second I green. So if we switched, let's say, if we switch these 2 letters, this I and this N, we get a different word. Okay, that's fine. But let me erase this. If we switched this letter and swapped them, so the green one came first and the red one came second, well, that's a repeat. It's still the same word. We have not, we've changed 2 letters, but we haven't come up with a new order. And this is because we have repeats. So the way we deal with repeats is we have to divide by how many different, how many repeats there will be for each object. Like, what will 2 I's do? How many repeats will 2 I's cause? Or we have, well, actually we have 3 I's in this word. How many repeats will 3 I's cause? Or how many repeats will 2 L's cause? And so the rule for this, if there are, let's say, N1, that's how many there are of the first object. And N2, that's how many there are of the second object. And N3 is how many there are of the third object, and so on. Then the total number of distinct or different arrangements is given by, well, before it was just n factorial, right? If everything was distinct and different, then there's n factorial different ways to arrange these objects. But if there are repeats, now we have to divide by how many repeats there are of each object, and that factorial. What I mean by that is, we start off with the word initially. It has 9 letters. So if there were 9 different letters, there would be 9 factorial ways to arrange them. But there's some repeats. There's 3 I's. So we divide by a 3 factorial. Because that's how many ways you could arrange the 3 I's. And we have 2 L's. So we divide by a 2 factorial. And that's basically it. If there are repeats, you divide by each repeated value factorial. Okay, and this just sort of ties together everything that we were just talking about. Now, moving on, the fundamental counting rule. So let's say you have n objects, but you don't use all of them. So let's say you have to make a password for your phone. You need a phone password. It has to be 4 letters. 4 letters long. So no numbers, no digits, just 4 letters. So let's say like position, let's go back here. Let's say like position 1, position 2, position 3, position 4. So like first letter, second letter, third letter, fourth letter. First, second, third, and fourth. You have to pick 4 letters for your password. Well, how many options do you have for that first letter? Well, there's 26 letters in the alphabet, so you have 26. Now, let's say, for example, in this password, you are not allowed to repeat letters. Well, you're picking 1 letter for the first, then there would be 25 letters left to choose for the second position in your password. And once you have 2 letters chosen, there's 24 letters left. And if 3 letters chosen, there's 23 letters left. And so that's what the fundamental counting rule is saying. Just the number of ways each step in the procedure can be done. And then we multiply those numbers together. So in this case, 26 times 25 times 24 times 23. That's how many different passwords there would be with no repeated letters. Or if it would really make no difference if there were if you were allowed to repeat letters, the numbers would just be different. Instead of 26, 25, 24, 23, it would be 26 times 26 times 26 times 26. And so the fundamental counting rule basically says to determine how many different ways a sequence of things could be done, you look at how many ways each individual step could be done one by one, and then you multiply those numbers together. All right, so that's the fundamental counting rule. And the fundamental counting rule is a little bit more versatile than the next 2 counting techniques we'll talk about, because with the fundamental counting rule, you could apply it when you are allowed to repeat objects, and you could also apply it when you're not allowed to repeat objects. Now, the next 2 counting techniques, permutations, which we'll talk about first, and combinations, which we'll talk about second. In both of these cases, the key is no repeats. You have no repeats. So permutations of objects from a group of distinct, now remember, distinct is important. There's different objects, like a deck of cards, 52 different cards, are ordered lists without repeats. All right, so how many case-sensitive 5-letter passwords are possible if repeats are allowed and are not allowed? If not are allowed, so we just talked about this on the last slide. The only difference here is we have the word case-sensitive. That makes it a little bit different because with case-sensitive, uppercase A and lowercase a are 2 different symbols. They're not the same. Uppercase, lowercase are different. So instead of having 26 letters, we have 52 because there's 26 lowercase and 26 uppercase. Now, if repeats are allowed, 52 options for the first letter in the password, 52 for the second, and so on, and so on, and so on. And if repeats are not allowed, just like in the last slide, instead of starting with 26, we start at 52, 52, 51, 50, 49, 48. These are called permutations. This is how many permutations there are of letters. So let's formalize this in terms of the notation and the formula. So we're using 2 variables here, n and r. N is how many total different objects you're starting with, and r is how many objects you're choosing. So that's like the subgroup or the subset of the n objects without replacement, no repeats, without replacement. So down here, the permutation of A, B, C and the permutation C, B, A are different. Same 3 letters, but they're different permutations. All right, so our notation for permutation is capital P. So I'm looking down here. Capital P with a lowercase n and a lowercase r subscripts. And the formula for permutation is n factorial divided by n minus r, in parentheses, factorial. So let's see how this formula works. Let's see what it looks like. Let's say, and this is going back to the very first question that we worked through. Let's say you have 15 students in the math club. In how many different ways can you select a president, a vice president, and a secretary? Now, I'll tell you right now, this is not something you want to count by listing. I believe it's going to be over 2,000 different ways this could be done. But we're looking for permutations from a set of 15 objects. Well, in this case, the objects are students. So first thing to observe, order matters. When you're doing the homework, when you're doing problems, you're not going to see the word permutation. You're not going to see the word combination. It's not going to say in the directions, how many permutations of this are there? How many combinations of this are there? You're going to have to, based on the context of the problem, you're going to have to read the problem and determine, is this problem talking about a permutation? So going back to I will go back a couple slides to the definition. Permutations. You're starting with n objects. You're picking r of them. No repeats, and order matters. Okay, so no repeats, order matters. It's a permutation. Okay. So going back to the 15 students, and we're picking a president, a vice president, and a secretary, and the order matters here. So we could apply the permutation formula, where n is 15 and r is 3. And our formula from the last slide, NPR for permutation. Well, in this case, it's 15P3. And the formula says that should be equal to 15 factorial divided by 15 minus 3 factorial. And we know 15 minus 3 is 12. So that's 15 factorial over 12 factorial. Now, what is 15 factorial over 12 factorial? Well, the factorial notation means on top, the top of the fraction, the numerator, that's 15 numbers. That's the numbers 1 through 15, all multiplied together. 15 times 14 times 13 times 12, da 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 da. On the bottom, in the denominator, we have 12 factorial. So that's the numbers 1 through 12 multiplied together. So if we have 15 times 14 times 13 times 12 times 11 times 10 all the way down to 1 on top, and on the bottom we have a 12 times 11 times 10 all the way down to 1 on the bottom, well, look what happens. We have the number, the 12s cancel, the 11s cancel, the 10s cancel. Actually, the numbers 1 through 12 on the bottom and 1 through 12 on the top cancel, and we're left with 15 times 14 times 13. And if we pop that into the calculator, we should get 2,730. I didn't actually use the calculator. I used Desmos. And I recommend Desmos, always I recommend Desmos over a handheld calculator. And when you're typing the permutation formula into Desmos, it's very simple. You have to type exactly this. You have to type a lowercase n, then an uppercase p, then a lowercase r. As soon as you do that, Desmos knows you're talking about permutations. And so in parentheses, you tell Desmos, out of 15 objects, I'm picking 3. And as soon as you type in the parenthesis, Desmos will give you 2,730. So the actual calculations are pretty simple if you're using Desmos. The difficult part, I think, is more interpreting the problem and determining what to do. So, recap. Permutations, you're picking a small group from a larger group. No repeats, order matters. And we could also sort of combine the permutation rule and the fundamental counting principle. So, for example, in how many ways can you select 2 letters followed by 3 digits? And digits are numbers and 0 through 9. So yeah, you have 10 digits. So of the 52 letters, you're picking 2 of them. And of the 10 digits, you're picking 3 of them. So in how many ways can you select 2 letters, letter, followed by 3 digits or 3 numbers? Well, we could look at this in terms of the fundamental counting principle, or we could look at this in terms of permutations. Excuse me. So in terms of, or we could look at it in terms of both. Let's look at this as a 2-part process. Part 1, pick the 2 letters. Part 2, pick the 3 numbers. So out of, and so repeats are not allowed, and that's key right there. That tells us it is a permutation. Well, the fact that repeats are not allowed and it's an ID. Obviously, if it's an ID, order matters. So when we're picking the letters, we're picking 2 out of 10. 2 out of the 10 digits. When we're picking we're picking the letters, it's 2 out of 26 letters. And then, so let's say that's out of 26 letters, we are picking 2 of them. And then we're picking the numbers. Well, we have 10 digits to choose from, and we are picking 3 of them. And the fundamental counting rule says, take this number for the first part, take this number for the second part, and multiply them together. Okay, so the part 1, 2 letters out of 26, there's 650 ways to do that. Part 2, there's 3 numbers out of 10, there's 720 ways to do that. Multiply, we have 468,000. All right, so that is permutations. Now let's move on to combinations. Similar to permutations, you're picking it's basically how many ways can you pick a small group of objects from a larger group of objects with no repeats. But the difference is unordered groups. So combinations, order does not matter. In how many ways can we select a 3-person team to represent our class of 26 students in a statistics competition? So the difference here is we're not selecting a president, a vice president, and a treasurer. We're just picking a committee or a team of 3 students. So before we solve this, one quick definition, more like a formula than a definition. So combinations, out of n objects, we're picking r of them, no replacement, no repeats. The only difference is rearrangements are the same. So ABC and CBA, those are not 2 different arrangements. Those are the same. Each of those is the same group. So this ABC and CBA is one possible group of 3. All right, so let's come back to the problem. We have 26 students. We want to, how many different ways can we select 3 of them? Well, one person can't be repeated. We can't have one person taking up 2 slots on the team. So we're picking a small group from a larger group with no repeats, but the key word here is team. It's just a team. It's just 3 people, no ranking, no hierarchy, no specific offices. So we could go back and we could apply the combination formula. And notice the combination formula is almost the same as the permutation formula. So the permutation formula is right here. That's NPR. The combination formula just has this extra r factorial at the bottom. All right, so n factorial divided by n minus r factorial times, in this case, r factorial. Okay, so in this case, the N is the 26, the R is the 3, and so we have 26 factorial divided by 26 minus 3 factorial, that gives us 23, times 3 factorial. Again, this goes right into Desmos. You just type in, just like with the permutations, lowercase n, capital C, lowercase r. As soon as you type that in, Desmos knows you're talking about combinations. And the calculations become very straightforward. All right, so a quick overview. When you're selecting a group of R objects from a larger group of N objects, if repeats are okay, you have to use the fundamental counting rule. If there's no repeats, well, it may be a combination, it may be a permutation. It depends on whether or not order matters. If order matters, it's a permutation. If order does not matter, it's a combination. And this is just another way of expressing sort of this flow chart. Permutations and combinations. In both cases, you're selecting, in this case, I'm using K instead of R. Some books use K, some books use R. I go back and forth. Sometimes my R's come out looking like N's, and I like using K better, but either way. As long as we define what's what, selecting K items out of N items. Permutations, order is important. Combinations, order is not important. Keywords, arrangements, that's telling you order is important. Subsets, groups, samples, selections. These words are key to saying that order is not important. All right, so that about does it. I just want to give you a preview into a problem that we'll do on another worksheet. So we have not talked about probability. This is the last slide in this set of notes. We have not talked about probability yet. I'll talk about probability on the next set of notes. This set was just counting. So again, like the first thing I said in this video, the essence at the core of probability is counting. So now that we've covered these counting techniques, now we could go back and start talking about probability. So for example, let's say you're dealt a hand of 5 cards from a standard 52 card deck. What is the probability of being dealt 4 aces? So we will address this problem in my next video. That's it for now. Probability with counting comes next.